Bismillahirrahmanirrahim. Hello everyone. Today in this tutorial I'm going to show you how to design BRB or buckling restrained brass. Recently some of subscriber asked me to design this BRB with pushover analysis and also with another method. So in this tutorial I'm going to use equivalent lateral force and also response spectrum analysis as well as pushover analysis, and then we will see how we can design this backline restraint frame. Backline restraint frame is very effective for stiffness and also earthquake resistant structure. If we have a tall building, so there is required have a brass system, but most of brass has a lacking of backling. So this can provide to fill this lacking. Now let's see, we have in the isosceles curve we have BRB, which is full curve in the tension area and also in the compression area. But we have a concentrically brass frame which has full curve in the tension but less in the tension. So this is the lack of CBF. The same ECBF is also the same isosceles curve. When we have to prevent from this condition, then we have to search for another way. The only way is to provide a sort of method which can prevent this leakage. So this is a BRB which has a core steel and unbounded concrete. The main point is the steel should yield, which we have to provide a very low strength steel, and the remaining part should be stable to resist the compression load. And recently a lot of companies producing and manufacturing these sort of brasses, and most applicable for retrofitting of existing structure and also strengthening the existing structure. So now we are going to design such brasses in ETABS software. We have a 2D frame, steel frame. We're gonna define first material. We define FY50, which is yield strength is 500 megapascal, and we have another for backling restrained brass, which are lower. We can make it more lower as much as we want, because if this be high, then there will not be any dissipation energy. So in this case we should provide lower yield strength, and then during an earthquake this core steel will yield. So finally the system dissipate more energies. Now for our case we assume this is okay, and going to define section. ETABS after version 15 it's developed and provide a new sort of BRB which we can find in this section. We go to the here. We including the BRB, we also have core brass BRB. That's a little different, but the work is same. We are going to check a SD section, going to OK, and from here then we can choose Star Seismic BRB. Star Seismic BRB is the Star is a company, Star Seismic, and BRB is the brass. So it has a lot of section from 1 inch square second core area to 52 inch square second square square inch steel area which is provided in the core. For designing, we will determine that amount. So here we are not going to the calculation, just we are using a sort of uh, we're going to add a type of auto selection system we called auto BRB. In auto BRB, we are going to select that buckling restrained brass, import here. So all this section will load in our auto brass. Then the program will calculate which one is uh, accurate for us. Yes, here we are, and we can add to our. Actually, it's too much, and we can add this few is okay and okay. And one more thing is we are going to add beam column section. So for beam column section, we are going to add wave flange, auto selection. This also should be auto no, auto call BC beam column. Then we are going to just select flange, and we don't have here, and we're going to import some B from this section, and we are using FEY 50, and here we can again so I'm going to use W. This is very small. Yeah, here we can choose a sort of this section and go to add to that. That's it. Okay. So now we have auto BC and auto BR. That's one more things in material we should do the hysteresis behavior of this material. This is steel. Here we go to the nonlinear material data, and from hysteresis type we should use BRB hardening. The BRB hardening is this behavior. If you are familiar with material property, then you understand what it means. So we use, and also other parameter. If you want a strain on seed on strain hardening, this parameter. But all these data where we can get from the manufacturing company or from experiment. And also this is acceptance criteria for performance of the system of the BRB. You can like immediate occupancy or life safety or collapse, you can change in the tension and the compression, but I will keep it in default. But if you have some research, some experiment data, then you can make compare with them and give the data what you got from the experiment. And the next thing is we should draw the beam columns. So we're going to select auto beam column. So this is it. I can go to here. Yes, it's called. This is beam column. Now the things I'm going to add boundary condition restraint. I can select pin or I can fix it. But this is still structure. It's better to use pin connection. That's it. The second is we are going to draw the auto BRB. So we're going to draw. It can be diagonal, or it can be in a chevron shape, or it can be in an X shape. What shape or what configuration you want is okay. But I'm going to use a diagonal shape. It's better to choose all the stories, and I'm going to use all the stories, then it can get through. And in this part I'm going to use vice versa, and going to again and delete this one, and I'm going to again and draw from here to here. Okay, and so the next thing is we should define hinge properties for buckling brass. We should select all the restrained buckling brass, and then we should go to define as assign in the frame section. We're going to hinge properties. In hinge properties, just select O2, and here we have ASC 71 code, and there is a beam column, and also we have brass. We're going to add 1 for one end, and 0 for one end, and 1 for another end. The same thing is this. Okay, done. Go to apply. Hinge properties is applied to each node. So, and everything is done. The second thing is I'm going to apply some load. This is hinge node. I'm going to apply some load, assign joint load forces. So it can be in a z direction, about 200 kilonewtons minus. And also I can go check progress and use about 200 live load. Okay, the next thing is if I go to do the pushover analysis, I have to define load section, hinge section to each beam column. But in this tutorial, I just use equivalent lateral force and then design this. And for next tutorial, I will apply pushover. In the load pattern, I'm going to define called EQ. I will choose automatic earthquake loading, or I will choose just one direction and add and go to. I'm going to turn off all this, and then going to these two X, Y, these two, and the short and this is California. Actually, this is location for California, these parameters, and I will accept this. And only thing is here is should be 7, because in ASC 7 they required it should be about 7. I think yeah, it should be in the first page. Yeah, here is it should be about 7. So I choose 7, and another parameter is okay. Just this EQ is X and Y. So the modeling and loading is completed. Just we are going to save the model. I'm going to the desktop and call BRB, and again I'm call BRB2. Now we'll run analysis. Model analysis getting some time because the restraint is not actually stable for this building, so we have to give a fixed boundary condition, then the model analysis will go quickly. Actually, the model analysis is taking so much time. I'm going to pause and fix. I'm going to cancel this. Going to cancel. The another analysis is actually I can go and set the analysis. It's not dynamic analysis, so we do not need to do model analysis. But before this, I'm going to define a combination because I forgot to define. I'm going to still design and can be convertible. And this is design is tail load and for steel, and last one also they consider the earthquake load, so it's okay. And but instead I'm going to add assign a joint called restraint, and it should be because it's 2D, so it means it will be very unstable. So okay, now this is time to run again. Now let's say this take too much quick time, because when you're doing a model analysis they will configure your model it's right or not. So now we are going to see the results of earthquake response. So I'm going to see this is earthquake response. So the maximum is very short because we have a BRB, so that's which is very high stiffness and also very strong for earthquake system. And also we can quickly to display the shear force. We are going to store shear force in EQ. So this is the maximum is about sorry, it's stiffness. I'm going to story shear. So this is the story shear is about, so very least, so about 30, which is called 31 kilonewtons, very small. And now in the same case we are going to save as this, and this is called without BRB. This is without BRB, and I'm going to BRB2 is also should be on, and here I'm going to do one more thing. I'm going to delete select I'm going to delete this BRB. That's it. So another parameter is I should check one, that load pattern, and we go to the EQ, which is for moment resisting steel resisting structure, that should be about 8. Then we can go to run this, and also we have here. Now we're going to compare the two results together. Or instead, we can use a concentric brass or another type of brass. This is also completed. We're going to display the response and going to the storage here, going to EQ. So now here is about minus 9. So it means actually we increased the R. So that's not right. When R is increased, so the shear force will be reduced. That's the recommend. For ordinary steel, we have about 3 or 5. Now I should change this load pattern. This should be about it's ordinary steel because we didn't define any specific joint. It be 4, and this is about 3. Okay, then we are going to run again. Now let's see the response of shear force. Going to EQ and going to storage shears. Now it's increased to about double because we reduced the R. So it's 18. Now we are going to see the so it's about 31. So this system increased the shear force. Now we are going to design. We should revise this. It's about called BRB frames, and the parameter is 7, and another parameter is okay. Then we go to automatic, and here we can come and see we're checking doing a revise, and this is not special. This is called ordinary moment resisting frame, and this is about 4. So we're going to OK and then run this. Here you say there we have to, because we have automatic, there is need some iteration to find the correct section. Yeah, fortunately the ordinary steel frame is passed. Now let's see what we got. So still is running. Yes, one more time. Let's see, 10 is left. Seven is left. Two is left. You press 1. Yes. Uh, the ordinary steel frame is design is done. We can see the section which is required. This top section is about in the collapse prevention, and this is in another beam. Everything is appropriate, and all the W 6 by 15, and also the column is 6 by 20. Now let's see the uh, restrained brass. We can see the result is the store BRB1, which is required 1 square inch, and this is beam is required a little high section, and also the column is but 5. I think in column in this was about 6. So this is the result. And also one more thing, we should check the displacement from both this maximum displacement using EQ. So the maximum displacement in the ordinary is about 23 millimeters, and for buckling-restrained frame is about, let's see, is about 2 millimeters. So this is the difference. So this is the difference, which is very effective for controlling the structural acceleration, displacement, and J ratio. This is the end of our tutorial, and the next tutorial will discuss how we can do pushover analysis with BRB or buckling restrained frame structure. Thank you for watching. If there is any question regarding this and theoretical calculation, and I can give some resource, especially you can check AISC design guide. You can find this BRB is also including the in this code, and you will find this and will be useful for earthquake resistant structure. And if you have any more suggestion or question, and put in the comment, I will get time and give you answer. Thank you again. Have a good time. See you next time.